Hi, I am Yuan Yuan, sharing our work on dimensionality of word embeddings. Our paper addresses an open problem in word embeddings. We know that translating words or sentences into vectors is the first and the most fundamental step of almost all natural language processing tasks. But for each token, how large should the vector be to capture adequate information? Well, in most studies, 300 is a common choice. Some other studies perform grid search to choose the optimal ones for their specific tasks. For most empirical work in word embeddings, there turns out to be a sweet spot, which is usually explained using either underfitting or overfitting. Surprisingly, as Professor Aurora says in his tutorial, there is so far not a good theoretical explanation to back up this intuition. So, how do we find a good dimensionality for word embeddings? Here is our solution. We first need a distance metric to quantify the differences between any two word embedding matrices. Then we choose a dimensionality to optimize over the embedding matrix's distance within oracle embedding. Starting with the distance metric, our goal is to quantify the distance between two word embedding matrices E1 and E2, where E1 and E2 can be of different dimensions. Also, it needs to capture the important characteristics of word relatedness and analogy. Hence, we propose pairwise inner product loss, which takes this form, for which we call pip loss. Now that we have a loss function, our next step is to decompose the loss function between an embedding matrix and its corresponding oracle embedding. We observe that most embedding algorithms are matrix vectorizations of some sort. With this observation, our main theorem approximates the loss function into a bias and variance term, where the spectrum lambda and noise sigma here can be estimated using statistical techniques. Thus, we just need to find the dimensionality that optimizes the right-hand side. Using this procedure, we calculate the optimal dimensionality for text 8 corpus and compare the p plus with the empirically optimal ones. As expected, their performances are very close. So the takeaway from our work is, first, we define the p plus, a novel metric that quantifies differences between word embedding matrices. Second, we propose a framework to find optimal dimensionality. Third, in our paper, we also quantify the robustness of some major embedding algorithms. Make sure to check out our dimensionality selection tools on GitHub. No need to worry about dimensionality when you perform your next NLP task. Thank you.